235 million people. That's how many Americans across 40-plus states have been paralyzed by Winter Storm Fern. While the evening news cycles through snowplow footage and cheerful meteorologists, 850,000 homes remain dark, silent, and freezing. 3 confirmed dead from exposure, but that number's climbing as the thaw reveals what the storm buried. Flight cancellations exceeded COVID-19 levels. Grocery stores stripped bare. 18 states declaring emergencies across a 2,000-mile scar from Texas to Maine. The question everyone's avoiding: why does this keep happening? More importantly, what aren't they telling you about Winter Storm Fern? Because the storm's physical damage, that's just the surface. Stay with me, and I'll show you the collapse unfolding beneath the headlines. Subscribe and follow along, because what unfolds in the coming days will determine whether this storm was an anomaly or evidence that our infrastructure has reached a breaking point we've been ignoring. Because when a weather system, aging grid components, and systemic neglect converge to paralyze a nation that survived countless winters before, that's not coincidence. That's a stress test we never prepared for. Something broke across America in the last 72 hours, and the cracks are still spreading. Winter Storm Fern didn't just sweep through the country, it exposed every fragile seam in the systems we've built our lives around. More than 235 million people felt its reach, 40 states and counting. The numbers sound abstract until you realize that's 7 out of every 10 Americans suddenly thrust into a scenario where the lights might not come back on, where the grocery store shelves are bare, where getting home becomes a gamble with your life. Right now, as you're hearing this, 850,000 homes sit in the dark. Families huddled around fireplaces and camping stoves. Elderly neighbors wondering if their medication will spoil in dead refrigerators. Children asking why the heat doesn't work. This isn't some distant catastrophe you scroll past on your phone. This is the infrastructure of the richest nation on Earth failing under weather that shouldn't have brought it to its knees. The airports tell their own story of collapse. More than 10,000 flights canceled. Not delayed, canceled outright. Rebooking systems crashed under the weight of desperate travelers trying to reach loved ones, trying to get home, trying to escape cities that had frozen solid. We haven't seen cancellation numbers like this since the height of the COVID-19 pandemic, when the entire world stopped flying. But this time there's no virus, no lockdown, no global emergency, just ice and wind, and a power grid that couldn't handle either. 18 states have declared emergencies. From Texas, where ice storms are supposed to be rare anomalies, all the way through Tennessee and Kentucky, up through the Midwest, across to the eastern seaboard, and into New England. A storm track that stretched 2,000 miles, carving through regions that thought they were prepared, and regions that never stood a chance. The question everyone keeps asking is simple, almost childlike in its directness. Why does this keep happening? The images coming out of affected areas don't match the sanitized weather warnings you see on the evening news. We're talking about supermarket shelves picked clean, not because people panicked, though some did, but because the trucks stopped coming. The supply chain doesn't just pause for weather anymore. It shatters. Distribution centers locked in ice. Drivers unable to navigate roads that became skating rinks in a matter of hours. Refrigerated goods rotting in warehouses without power. The invisible machinery of daily life grinding to a halt while meteorologists shrug and say the storm was well within predicted parameters. You want to know what that looks like on the ground? Picture a grocery store in Memphis at 7 in the morning, the day after the storm hit hardest. The bread aisle is empty, except for a few bags of hamburger buns nobody wanted. The milk coolers are dark and warm. Entire sections cordoned off with yellow tape, because without refrigeration, the food is already spoiling. A woman stands there with 2 children, staring at shelves that should be full, and she's not panicking. She's calculating. How long can she stretch what's in her pantry? Does her neighbor have formula for the baby? When will things go back to normal? But here's the thing that should terrify you. This storm wasn't unprecedented by historical standards. Yes, it was large. Yes, it was disruptive. But the meteorological data shows this kind of system has happened before, will happen again, and shouldn't be capable of bringing American infrastructure to a standstill. So why did it? The power failures tell a more disturbing story than the storm itself. We're not talking about a few trees falling on power lines in a rural county. We're talking about cascading grid failures across multiple states, transformers exploding under ice load, entire regional systems going dark because one critical node failed and the dominoes kept falling. Engineers have been warning about this for decades. The grid is old, fragmented, vulnerable to exactly this kind of stress. And yet, year after year, storm after storm, the same failures repeat while politicians promise upgrades that never quite materialize. 3 people are confirmed dead from cold exposure so far. 3 that we know about. That number will climb as the thaw continues, and searchers find the bodies of people who sought shelter in cars, in sheds, in places that seemed safe until they became tombs. One of them was a man in his 70s, found in his home 48 hours after the power went out. No heat. No way to call for help because the cell towers were down. He died alone, in a house that should have protected him, in a country that should have kept the lights on. The mainstream coverage focuses on snowfall totals and wind speeds, dramatic footage of snowplows clearing highways, cheerful reporters standing in blizzards, proving they can still broadcast. What they're not showing you is the infrastructure collapse happening in slow motion behind the spectacle. The water treatment plants running on backup generators that might fail. The hospitals operating at reduced capacity because staff can't get to work. The nursing homes where residents sit in near-freezing rooms because the heating systems need electricity to function. The disabled residents whose medical equipment is now useless plastic and metal. We've built a civilization on the assumption that certain things just work. You flip a switch, the lights come on. You turn a tap, water flows. You drive to the store, there's food. These aren't luxuries, they're the baseline of modern existence. And Winter Storm Fern just revealed how quickly that baseline can dissolve. The storm's geographic reach defies easy categorization. This wasn't a regional event you could contain with local resources. States from the Gulf Coast, where freezing rain is a once-in-a-decade event, got hammered just as hard as northern states, with snow removal budgets larger than some countries' GDPs. The system moved with a kind of brutal efficiency, exploiting every weakness in America's patchwork infrastructure, finding every gap in preparedness, punishing every delayed upgrade and deferred maintenance decision. So the question that opens this investigation isn't just about weather. It's about why a storm of this scale, large but not apocalyptic, severe but not outside historical norms, managed to paralyze a superpower. Is this just bad luck compounding with poor planning? Is it evidence of systemic negligence? Decades of choosing profit over resilience? Or is there something else happening here? Something in the storm's behavior or our response to it that we're not seeing yet? Because what comes next in this story isn't just about ice and wind. It's about the data that doesn't quite add up. The infrastructure vulnerabilities that keep getting exposed. The climate patterns that seem to be shifting in ways our models didn't predict. And the uncomfortable possibility that what we're calling a natural disaster is actually a stress test we're failing. The aftermath is still unfolding. The full human cost is still being counted. And what you're about to discover is that the real story of Winter Storm Fern isn't what happened during the storm. It's what the storm revealed about the fragility underneath everything we take for granted. The official death count stands at 3, but anyone with experience in disaster response will tell you that number is a placeholder, a minimum, a figure that will grow as the ice melts and the searches expand. Cold kills in ways that aren't always immediate. aren't always obvious and aren't always counted in the first wave of reporting. Hypothermia doesn't announce itself with drama. It creeps in, shuts down the body degree by degree, and leaves behind victims who simply look like they fell asleep. One of the confirmed deaths was a 58-year-old woman in rural Kentucky. She left her house to check on her horses during the height of the storm. Temperature was 19 degrees Fahrenheit, wind chill closer to zero. She made it to the barn, got the animals secured, started back toward the house. Somewhere in that 100-yard walk, she slipped on ice, hit her head, couldn't get up. Her husband found her 3 hours later when he realized she hadn't come back. By then, exposure had done its work. The medical examiner ruled it accidental death by hypothermia with contributing head trauma. The storm didn't kill her directly. It created the conditions that made every small mistake fatal. But here's what the death statistics don't capture: the near misses, the people who survived by minutes or luck or the kindness of strangers. A family of 4 stranded in their car on Interstate 40 in Tennessee for 18 hours. No heat. Kids in the back seat wrapped in every piece of clothing they packed for what was supposed to be a quick trip to visit grandparents. The father kept the engine running in short bursts to preserve gas, terrified of carbon monoxide poisoning, but more terrified of freezing. They were rescued when a snowplow crew spotted their hazard lights through the whiteout. The youngest child, a 6-year-old girl, was hypothermic when they reached the hospital. She survived. The incident won't appear in any death toll, but it was that close. The National Guard mobilized across 17 states, the largest cold weather deployment in recent memory. Soldiers going door to door in neighborhoods without power, checking on residents, transporting the vulnerable to warming shelters. But even military logistics strain under these conditions. Roads impassable, communication networks down, resources spread thin across thousands of square miles. A Guard unit in Tennessee spent 6 hours trying to reach a nursing home that had lost power, only to find the facility had been evacuated 2 hours earlier by local fire departments who couldn't wait for help that might not arrive. Power outages in winter aren't just inconveniences, they're life support systems failing. No electricity means no furnaces, no electric heaters, no way to warm a building designed to be climate controlled. It means water pipes freeze and burst, flooding homes with water that then turns to ice. It means sump pumps stop working, so basements flood. It means medical equipment shuts down, oxygen concentrators, CPAP machines, motorized wheelchairs, refrigerated medications. People with chronic conditions become acute emergencies overnight. An elderly couple in Michigan, both diabetic, both dependent on refrigerated insulin. When their power went out and stayed out for 36 hours, they faced an impossible calculation. The insulin would spoil without refrigeration. They couldn't get to a pharmacy because the roads were impassable and the pharmacies were closed anyway. A neighbor with a gas-powered generator let them store their medication in his refrigerator, but not everyone had that option. How many diabetics across the affected region lost access to insulin? How many people with other temperature-sensitive medications, chemotherapy drugs, biologics, vaccines, watched their life-sustaining supplies become useless? The psychological toll layers on top of the physical danger. Isolation amplifies fear. When your phone dies and you can't charge it, when the landline doesn't work, when you haven't seen another person in 48 hours and don't know if help is coming, your mind starts creating catastrophes to fill the void of information. People rationing candles in the dark, counting the hours of fuel left in the generator, lying awake listening to tree branches snap under ice load, and wondering if the next crack will be the one that crashes through the roof. Families got separated by outage zones that divided cities like borders on a map. One side of a neighborhood with power, the other side dark. Parents at work when the storm hit, unable to get home to children who were alone and scared. Elderly parents living independently, suddenly unreachable by phone, and their adult children stuck in other states, calling police departments and fire stations, begging for welfare checks, getting put on hold or told resources were prioritized for life-threatening emergencies. Emergency services measured their response times not in minutes, but in hours. Ambulances trapped behind jackknifed semis on icy highways. Paramedics arriving at cardiac arrest calls to find patients who'd been down for too long because the 911 system was overwhelmed and dispatch was triaging desperately. Fire departments responding to carbon monoxide poisoning calls. Whole families overcome by fumes from generators run indoors. From charcoal grills burned in living rooms for heat. From cars idling in attached garages. This is where desperation breeds danger. People know running a gas generator inside will kill them. But when the temperature in your house drops to 35 degrees and your children are shivering uncontrollably, rational thinking gives way to immediate need. You crack a window. Tell yourself that's enough ventilation. Fire up the generator in the basement or the garage and hope the carbon monoxide detectors work, assuming you have them, assuming they have batteries. Then, you fall asleep because you're warm for the first time in 2 days, and you don't wake up. First responders found multiple families this way. The news reports it as tragic accidents. The truth is, these are deaths caused by infrastructure failure, forcing impossible choices. The unhoused population bore the brunt in ways that won't make official statistics. Shelters opened emergency capacity, but you have to reach the shelter first. In cities where overnight temperatures hit single digits, people freezing to death in tents, under overpasses, in the doorways of closed businesses. Social services stretched beyond breaking. Outreach teams trying to find rough sleepers in areas they knew people camped, but the storm scattered everyone, forced people into hiding spots that became traps. The body count from this demographic will trickle in for weeks. But there were moments of grace amid the catastrophe. Neighbors sharing generators, taking in strangers who had nowhere else to go. A woman in Ohio opened her home to 14 people from surrounding houses when her gas furnace kept running after everyone else lost heat. They cooked on her stove, shared food, slept on floors and couches, and kept each other sane for 3 days. Communities self-organized warming centers in churches and community centers that had backup power. People checked on the elderly, shared supplies, created networks of mutual aid that functioned better than official emergency response. The human cost of Winter Storm Fern is still being calculated. For every confirmed death, there are dozens of near deaths, hundreds of injuries, thousands of traumatic experiences that will echo through lives for years. And underneath all of it runs a current of anger and bewilderment. How did we end up here? Why weren't we better prepared? Who decided our infrastructure could be this fragile? Because what you're starting to see is that this wasn't just a storm. It was an audit. A brutal, indifferent examination of every system we depend on. And we failed. The power grid didn't fail because of some dramatic single point of catastrophe. No massive explosion, no targeted attack, no unprecedented surge that broke transformers across the country. It failed the way complex systems always fail. Incrementally, predictably, and in ways that engineers have been warning about for decades. What Winter Storm Fern exposed wasn't a new vulnerability. It was the same old vulnerability we keep ignoring until the bill comes due. Ice accumulation on power lines doesn't look dramatic until you understand the physics. A 1/4 inch of ice coating on a transmission line can triple its weight. Lines designed to carry specific loads suddenly bearing forces they were never meant to handle. The wires sag. The sag increases the surface area for more ice to accumulate. The weight increases. Something has to give. Either the line snaps, or the weight pulls down the poles and towers supporting it, or the ice-laden line swings in the wind and touches something it shouldn't. Another line, a tree branch, a metal structure, and creates a short circuit that cascades through the system. In Tennessee alone, More than 300,000 customers lost power at the peak of the outage. Utility companies reported hundreds of downed lines, dozens of damaged substations, transformers that exploded under load or failed from ice damage. The restoration timeline stretched into days, then weeks for some rural areas. But Tennessee wasn't unique. Similar scenarios played out across Kentucky, where ice storms hit infrastructure that had been upgraded after similar failures in 2009 and 2015. The upgrades apparently weren't enough. Texas presented its own nightmare scenario. The state's grid, famously independent from the national interconnected systems, struggled with ice accumulation and demand surges as millions of residents cranked up electric heating to combat temperatures that plunged well below normal. Deja vu from the February 2021 freeze became impossible to ignore. Different season, different storm system. Same result, a grid that couldn't handle extreme weather stress. Grid operators issued appeals for conservation. Some areas went dark anyway. The political recriminations started before the ice even melted. But the grid failures triggered dominoes that toppled into every other infrastructure system. Water treatment plants depend on electricity to run pumps, filtration systems, chemical dosing equipment. When the power goes out, water pressure drops. Boil water advisories get issued across entire counties. Except people can't boil water without power unless they have gas stoves. And even then, low water pressure means nothing comes out of the tap anyway. Bottled water sells out instantly. Stores can't restock because the trucks can't get through. The loop closes. Transportation infrastructure collapsed in stages. Airlines started canceling flights 36 hours before the storm hit. Standard precautionary measures. But the volume of cancellations overwhelmed rebooking systems. Passengers stranded in airports that lost power mid-crisis. De-icing operations at northern airports ran out of chemicals. Runways closed. Ground crews couldn't work in dangerous wind chills. The backup crew rotations that were supposed to cover for delays got stuck in cities where they'd flown in before the storm hit. Pilots timed out. Federal regulations limit how many hours they can work. So even when planes were ready, crew availability became a bottleneck. Rail systems fared slightly better, but not by much. Freight trains carrying essential supplies got delayed or halted entirely on ice tracks. Passenger rail services cut schedules dramatically or suspended operations. The trucks that haul 70% of American freight sat idle in parking lots because drivers couldn't safely navigate roads, and loading docks were closed anyway. Just-in-time logistics, the efficiency innovation that eliminated warehousing and inventory storage to cut costs, became a catastrophic liability when the timeline broke. You want to understand supply chain fragility? Look at the path a gallon of milk takes from dairy farm to your refrigerator. Cows get milked. Milk goes into refrigerated tanks. A truck picks it up and drives to a processing plant. The plant pasteurizes and bottles it. Another truck takes it to a distribution center. A third truck delivers it to your local store. Employees stock it in refrigerated cases. Every step depends on electricity, functioning vehicles, passable roads, and workers who can get to their jobs. Break any link and the milk never arrives. During Winter Storm Fern, multiple links broke simultaneously. Grocery stores in affected areas looked like something from a disaster movie. Produce sections empty, meat departments bare. Dairy cases dark and warm. Bread shelves stripped. But this wasn't panic buying. Well, not entirely. This was supply disruption meeting demand that couldn't decrease. People still need to eat during a storm. Probably need to eat more, since they're burning calories trying to stay warm in houses without heat. But the food isn't coming because the trucks aren't running, because the roads aren't passable, because the plows can't keep up, because the salt stockpiles are running low, because the salt comes from mines that ship by rail, and the trains aren't running. The interdependencies become dizzying when you trace them out. No power means gas stations can't pump fuel, which means generators run out of gas, which means more homes go cold, more businesses close, more emergency equipment sits useless. No power means communication towers drain their backup batteries, and cell service goes dark. No cell service means people can't coordinate, can't call for help, can't let loved ones know they're alive. No communication means emergency services respond slower because they can't get accurate information about where help is needed most. Traffic signals without power create chaos at intersections. Four-way stops work fine when traffic is light and visibility is good. They break down fast when roads are icy. Visibility is near zero, and drivers are panicking. Accidents block roads. Emergency vehicles can't get through. The accidents don't get cleared because tow trucks are busy or can't reach the scene. The traffic backup spreads. More accidents happen. The chaos compounds. Government preparedness faced a harsh reality check. Some states activated emergency operation centers well before the storm hit, prepositioned National Guard units, coordinated mutual aid agreements with neighboring states. Others scrambled reactively, issuing emergency declarations after the damage was done, calling for federal assistance when local resources were already overwhelmed. But even the best prepared states couldn't overcome infrastructure that wasn't built to handle this kind of stress. Private sector readiness varied wildly. Some utility companies had pre-staged repair crews from other states, stockpiled equipment, planned restoration priorities. Others waited to see how bad it would get, lost communication with field crews, and spent the first critical hours just trying to assess damage. Airlines with robust contingency planning still couldn't overcome the sheer volume of cancellations and the compounding delays. Supply chain companies with redundancy built into their logistics watched those redundancies evaporate as every backup route and alternate facility faced the same storm conditions. Grid specialists have been saying for years that American electrical infrastructure is vulnerable exactly like this. The American Society of Civil Engineers gives the nation's energy grid a C- grade, functional but increasingly unreliable, in need of massive investment to modernize and harden against extreme weather. The cost estimate for comprehensive upgrades runs into the hundreds of billions of dollars. The political will to spend that money exists in speeches and committee hearings, but not in appropriations. So instead, we run the grid at capacity, defer maintenance, patch problems as they emerge, and hope the next storm isn't too severe. Winter Storm Fern called that bluff. It wasn't even an unprecedented storm, just a large one, and it still brought the system to its knees. This wasn't a storm failure. This was a systemic exposure, a revelation that the infrastructure holding modern American life together is more fragile than anyone wants to admit. And the terrifying part, this will happen again. The next storm, the next heat wave, the next severe weather event will find the same cracks, exploit the same weaknesses, unless something fundamental changes. But before we get to solutions, we need to understand what made this particular storm so devastating. Because when you look past the immediate damage, past the predictable failures of aging infrastructure, there are questions that don't have comfortable answers. The storm's path makes meteorologists pause when they trace it on a map. 2,000 miles from the Gulf Coast to New England. 40 states affected. A single weather system maintaining coherence and intensity across geographic scales that usually tear storms apart. You ask a climatologist about it, and they'll explain the jet stream configuration, the polar vortex interaction, the atmospheric moisture content. All true, all documented. But the way this particular system moved, the duration it maintained, the intensity it sustained, it sits at the edge of what models predicted it could do. Early forecasts underestimated the ice. Not the snow totals, those came in close to predictions, but the freezing rain, the sleet, the glaze ice that coated everything from power lines to pine trees to parking lots. Some models showed it phasing through quickly, Others indicated a longer duration, but less intensity. What actually happened was the worst-case scenario from the models that no one quite believed would materialize. Forecasters adjusted predictions upward as the storm approached, but by then, preparation time had collapsed. Why did the models miss? Weather prediction isn't a perfect science. It's numerical approximation of chaotic atmospheric dynamics using incomplete data fed into equations that simplify reality. Small errors in initial conditions compound through the forecast period. We accept that 5-day forecasts carry uncertainty, but this was a 48-hour miss on critical precipitation type in a storm system the models had been tracking for a week. That's unusual enough to warrant questions. The jet stream behavior gets particularly interesting when you dig into the meteorological details. Some research suggests the jet stream isn't necessarily more erratic now than it was in the mid-20th century, which challenges common climate narratives about amplified polar vortex disruptions. But even if the overall pattern isn't unprecedented, the specific configuration during Winter Storm Fern, a deep trough pulling Arctic air south while moisture streamed up from the Gulf of Mexico, created conditions for prolonged ice accumulation across an unusually broad geographic zone. Polar vortex interactions are supposed to be reasonably well understood. Cold air normally confined to Arctic regions gets pushed south when the vortex weakens or becomes disrupted. This happens. It's documented. It's predictable in general terms. What's less predictable is exactly where the cold air will plunge, how long it will persist, and what other atmospheric features it will interact with. Winter Storm Fern represented a confluence of factors that individually are understood, but collectively created outcomes the models didn't quite capture. Communication breakdowns between meteorological agencies and the public added confusion. Weather warnings focused heavily on travel impacts, stay off the roads, avoid unnecessary trips, winter storm warnings in effect, all necessary information. But the messaging didn't adequately convey the infrastructure risk. People understood they might get snowed in for a day. They didn't understand they might lose power for a week. The gap between weather warning and survival preparation became critical for thousands of households that didn't stock supplies or prepare alternate heating because they thought this was just another winter storm. Now, we enter territory where speculation must be framed very carefully, because social media during and after the storm filled with theories ranging from plausible to absurd. Could weather modification technology have played a role? The short answer is no credible evidence links any weather modification to Winter Storm Fern. The longer answer is more nuanced. Cloud seeding technology exists. It's used in some regions to enhance precipitation or suppress hail. But the scale and sophistication required to create or steer a storm system of this magnitude is beyond any publicly known technology. Suggesting otherwise without evidence isn't investigation, it's conspiracy theory. That said, the fact that people ask these questions reveals something important about public trust and information gaps. When official explanations feel incomplete, when models miss critical predictions, when the scope of impacts seems disproportionate to the cause, people search for hidden factors. The intellectual error isn't in questioning, it's in accepting dramatic explanations without demanding proportional evidence. What's more interesting than conspiracy theories are the genuine data gaps in how we collect and share meteorological information. Weather models depend on observational data from satellites, weather balloons, ground stations, aircraft reports, and oceanic buoys. Coverage is imperfect. Entire regions, especially over oceans, polar areas, and developing nations, have sparse monitoring. Missing data points mean model uncertainty. During Winter Storm Fern, some meteorologists noted that offshore atmospheric conditions preceding the storm weren't as well sampled as they'd like. Did that contribute to forecast errors? Possibly. Can we quantify it? Not easily. Power grid telemetry presents even deeper data gaps. When utilities report outages, They typically provide customer counts and broad geographic areas. What they don't share is detailed data about which specific equipment failed, why it failed, whether the failure was predictable based on maintenance records, and whether similar vulnerabilities exist elsewhere in the system. This information is proprietary. It's also essential for understanding systemic risk. The public gets told 850,000 homes are without power. They don't get told that 12 substations failed because transformers hadn't been upgraded since 1986 and were operating beyond their designed lifespan. Delayed reporting on outage causes creates information, voids that speculation fills. Utility companies focus on restoration first, investigation later. Understandable from an operational standpoint, frustrating from a transparency perspective. Days or weeks after the storm, some utilities will release reports detailing failure modes and contributing factors. By then, public attention has moved on, and the lessons get archived in technical documents few people read. Airline operational data is similarly opaque. We know 10,000 flights were canceled. We don't know the decision-making process behind those cancellations, the threshold criteria airlines use, whether some carriers canceled more aggressively than others to avoid downstream cascading delays, or whether equipment and crew positioning failures made the situation worse than it needed to be. Airlines treat operational details as competitive information. The flying public treats it as customer service failure. Neither side gets full transparency. Some local news outlets showed raw footage of crisis conditions, stranded motorists, overwhelmed shelters, empty grocery stores, while national coverage recycled stock footage of snowplows and scenic winter landscapes. The selective reporting wasn't necessarily malicious, but it created a perception gap. People experiencing the crisis felt ignored or misrepresented. People outside the affected areas underestimated the severity. The disconnect between ground truth and broadcast narrative feeds distrust. The psychology of incomplete information is well studied. Humans hate uncertainty. When information is missing or contradictory, we construct narratives to fill the gaps. The narratives we choose say more about our existing beliefs than about objective reality. Climate skeptics see a cold snap and declare global warming debunked. Climate activists see infrastructure failure and declare this the new normal of climate chaos. Both reactions oversimplify complex systems for ideological comfort. Some atmospheric research genuinely does raise questions worth investigating. Why did this storm maintain intensity across such a long track? Are there feedback mechanisms between ice accumulation and storm structure that models don't fully capture? Could subtle changes in atmospheric composition or ocean temperatures have contributed to unexpected behavior? These are scientific questions requiring data analysis, not speculation requiring belief. The black box problem in pre-event modeling can't be ignored. Meteorologists constantly adjust forecasts as new data arrives. That's good scientific practice. But it makes post-event analysis difficult because the forecast everyone saw at time T-minus 48 hours was different from the forecast at T-minus 24 hours, which was different from the forecast at T-minus 12 hours. Which forecast should have triggered which preparedness actions? When did the certainty cross the threshold from possible to probable to imminent? These aren't academic questions. They're survival questions for people deciding whether to evacuate or shelter in place. Counterbalancing speculation with actual atmospheric science is critical. Researchers studied jet stream dynamics, polar vortex behavior, extreme weather attribution, and climate-weather interactions using rigorous methods. Their findings sometimes confirm our intuitions, sometimes challenge them, and often reveal complexity that resists simple narratives. Winter Storm Fern will eventually get the full scientific analysis treatment, peer-reviewed papers examining its development, path, intensity, and impacts. Those papers will be more reliable than social media theories, but they'll also be less satisfying because they'll trade drama for precision. The real story emerging from data gaps isn't conspiracy, it's fragmentation. We have incredible technology for monitoring weather, but imperfect coordination in sharing data. We have sophisticated models, but communication failures in translating forecasts into actionable public guidance. We have critical infrastructure, but inadequate transparency about its vulnerabilities. These aren't mysteries requiring elaborate theories, they're policy failures requiring political will to fix. What happened during Winter Storm Fern wasn't hidden. It was documented by thousands of people living through it. Recorded by meteorological instruments, visible in satellite imagery. But the full picture remains fragmented across jurisdictions, agencies, and private companies that don't share information seamlessly. Assembling that picture requires effort most people don't have time for, and access most people don't have clearance for. So, the uncomfortable truth is that in every disaster, the unseen data defines the real story more than the dramatic footage. And right now, most of that data remains unseen, not because it's secret, but because the systems for sharing it don't exist or don't function. Which brings us to the climate question everyone's dancing around. Here's where people's brains short circuit. The world is warming. Global average temperatures are rising. Arctic sea ice is declining. Glaciers are retreating. These are measured facts, not debatable opinions. And yet, Winter Storm Fern dumped historic amounts of ice and snow across regions that experienced brutally cold temperatures. The cognitive dissonance is real, and it's exploited ruthlessly by people selling climate narratives in either direction. Let's establish the foundational concept with brutal simplicity. Local weather is not global climate. Saying, "It's cold today, so global warming is fake," makes as much sense as saying, "I ate lunch, so world hunger doesn't exist." The Earth is massive. Climate is the average of weather patterns across the entire planet over decades. A single storm system, regardless of how large or intense, is a data point, not a trend line. But explaining why cold snaps don't contradict warming requires nuance that gets lost in soundbite culture. So here's an analogy that might help. Imagine a pot of water on a stove. As you heat it, the average temperature rises steadily. But the water doesn't heat uniformly. Convection currents create hot spots and cool spots. Bubbles rise. The surface temperature fluctuates even as the overall system absorbs more energy. Earth's climate system is infinitely more complex than a pot of water, but the principle holds. Adding energy to the system increases average temperatures while also intensifying variability. Arctic oscillations and polar vortex disruptions provide the mechanism for extreme cold outbreaks far south of normal. The polar vortex is a band of strong winds high in the atmosphere that normally keeps extremely cold air confined around the Arctic. When this vortex weakens or becomes disrupted, the containment fails. Arctic air spills south into mid-latitudes, bringing temperatures that feel apocalyptic because they're 40 or 50 degrees below normal for those regions. What causes vortex disruptions? This is where the science gets complicated, and the research shows nuance that resists simple narratives. Some studies suggest that rapid Arctic warming, the Arctic is warming roughly twice as fast as the global average, could weaken the temperature gradient that maintains the polar vortex. Less gradient, weaker vortex, more frequent disruptions sending cold air south. Other research indicates that the jet stream's waviness isn't necessarily increasing compared to mid-20th century patterns, which suggests natural variability plays a larger role than anthropogenic forcing in these specific events. The scientific debate here is real and unresolved. Climate scientists don't have perfect consensus on whether human-caused warming is making polar vortex disruptions more frequent or more severe. What they do agree on is that the Arctic is warming dramatically, that this warming affects atmospheric circulation, and that the impacts are complex and regionally variable. But here's the climate amplification mechanism that's less disputed. A warmer atmosphere holds more moisture. Physics demands it. For every 1 degree Celsius increase in temperature, the atmosphere can hold about 7% more water vapor. More moisture in the air means more fuel for precipitation. When temperatures do drop into the range where precipitation falls as snow or ice, the increased moisture content can produce heavier snowfall than would occur in a cooler, drier atmosphere. This is the paradox that breaks people's brains. Warming leads to more intense snowstorms. It sounds contradictory until you understand the mechanism. The snow doesn't fall because it's warmer. It falls because there's more moisture available. And when temperatures are right for snow, that moisture produces bigger, wetter, more intense winter storms. Ice storms in the south expose another dimension of climate impact. Historically, the Gulf Coast and Deep South experienced freezing precipitation rarely, once or twice a decade at most. Infrastructure wasn't built for it. Cultural knowledge of how to handle it didn't exist. But as climate patterns shift, the southern reaches of winter storms have been producing ice more frequently. Not every year, not predictably, but enough that what used to be once-in-a-generation events might become once-in-a-decade events. For infrastructure and populations unprepared for ice, this shift is catastrophic, even if the absolute number of events remains low. Multiple climate science hypotheses exist around Arctic sea ice loss and its downstream effects. Less sea ice means more heat absorption by dark ocean water instead of reflection by white ice. This local heating affects atmospheric circulation patterns. Does it make the jet stream wavier? Does it increase the frequency of blocking patterns that stall weather systems in place? Does it change the timing or intensity of seasonal transitions? Research is ongoing, and different studies reach different conclusions. Presenting this as settled science does the nuance a disservice. Historical parallels matter for context. The winter of 1977 to 1978 saw catastrophic cold and snow across much of the eastern United States. The winter of 1993 to 1994 brought massive ice storms to the south. The polar vortex event of January 2014 sent wind chills to minus 50 degrees Fahrenheit across the Midwest. Extreme winter weather happened before recent decades of rapid warming. The question isn't whether these events occurred historically. They did. The question is whether their frequency, intensity, or duration is changing. Some regions have experienced what climate scientists call a warming hole. Areas that have cooled or warmed less than the global average, even as the planet overall heats up. The southeastern United States showed this pattern for several decades, though recent years have seen that trend reverse. These regional variations complicate public understanding because people's lived experience of "it's colder than it used to be" or "winters aren't as harsh as when I was a kid" may both be accurate for specific locations while being unrepresentative of global trends. Winter Storm Fern serves as a teaching moment precisely because it resists simplistic interpretation. This wasn't a storm you can point to and say, "See climate change," or "See climate hoax." It was a complex meteorological event resulting from atmospheric patterns that are influenced by, but not wholly determined by, long-term climate trends. Treating it as proof of any particular narrative misses the opportunity to understand what actually happened. The science of extreme weather attribution has become sophisticated enough to estimate the probability that specific events were made more likely or more intense by anthropogenic climate change. Researchers use model ensembles to simulate how often and how intensely an event like Winter Storm Fern would occur in a world without human-caused warming versus the actual world. These attribution studies take months or years to complete and require careful statistical analysis. Jumping to conclusions before that analysis happens is premature. What we can say with confidence is that the climate system is changing, that the changes involve both warming trends and increased variability, and that extreme events, whether hot, cold, wet, or dry, are occurring against a background of rising global temperatures. We can also say that infrastructure designed for historical climate patterns is increasingly vulnerable as those patterns shift. Whether a specific storm was caused by climate change is often the wrong question. The right question is whether our preparedness assumptions based on past climate are still valid. Winter Storm Fern didn't need climate change to happen. Weather systems of this type have occurred throughout recorded history, but the context in which it occurred, warmer oceans providing more moisture, Arctic conditions potentially affecting atmospheric circulation, infrastructure aging beyond its design lifespan, populations concentrated in vulnerable areas, creates conditions where the impacts of such storms may be more severe than they would have been decades ago. The climate conversation around Winter Storm Fern should move beyond simplistic blame or denial toward difficult questions about adaptation and resilience. If extreme weather events of all types are becoming more common or more intense, how do we harden infrastructure to withstand them? How do we improve forecasting and communication? How do we build social systems that support vulnerable populations when disasters strike? These questions matter regardless of what percentage of causation you assign to human activities versus natural variability. But there's a universe beyond our weather, beyond our climate, that offers perspective on the patterns we're struggling to understand here on Earth. Astronomers using the Atacama Large Millimeter Array recently captured images that reveal planet formation in stunning detail. The teenage years of planetary systems, when worlds are coalescing from disks of dust and gas orbiting young stars. The images show gaps and rings in protoplanetary disks, carved by the gravitational influence of forming planets sweeping up material in their orbital paths. This is how solar systems are born, chaotic, turbulent, gradually organizing into the structured planetary arrangements we observe. The process isn't gentle. Dust particles collide and stick together through static electricity and weak gravitational attraction. As clumps grow larger, their gravity becomes stronger, pulling in more material faster. Collisions between growing planetesimals can shatter them or merge them, depending on speed and angle. Gas giants form in the outer disk, where ice and volatiles are abundant. Rocky planets form closer to the star, where only metals and silicates survive the heat. The entire process takes millions of years and involves constant, violent chaos, gradually settling into orbital harmony. What strikes you when you study these images is the presence of patterns, repeating structures across different stellar systems, rings at similar distances, gaps carved by planets of predictable masses, disk shapes that follow mathematical distributions. The chaos isn't random. It's governed by physics, gravity, angular momentum, thermodynamics, complexity emerging from simple rules applied over vast scales and time periods. You can draw thematic parallels to Earth's atmospheric systems. Weather is chaotic in the colloquial sense, unpredictable, variable, seemingly random from day to day, but it's governed by fluid dynamics, thermodynamics, and energy transfer. Air masses move because of pressure gradients. Storms form because of moisture and instability. The specific timing and path of any individual storm may be unpredictable beyond a few days, but the general patterns, jet streams, seasonal cycles, climate zones, emerge from underlying physical laws. Winter storm. Fern's swirling cloud patterns, visible in satellite imagery, mirror the spiral structures in protoplanetary disks. Not because weather and planet formation are the same process, but because both involve fluids and gases moving under the influence of rotation and pressure gradients. Turbulence looks similar across scales because the mathematics describing it shares deep structure. Visual metaphors help communicate complex science. Imagine a protoplanetary disk as a cosmic weather system. Material spirals inward toward the star, like air masses spiraling into a low-pressure center. Density waves propagate through the disk, like sound waves through the atmosphere. instabilities grow, creating clumps and vortices. Over time, the system evolves toward lower energy states, planets in stable orbits, weather systems that dissipate or mature. Climate science underwent similar expansion. Early models treated Earth's atmosphere simplistically, assuming uniform conditions and steady states. As observations improved and computing power increased, models incorporated more complexity: ocean-atmosphere coupling, ice albedo feedbacks, cloud microphysics, vegetation interactions. Each refinement revealed new mechanisms and new unpredictabilities. Our understanding deepened while our certainty decreased, a pattern familiar across many scientific fields. Expert voices in astronomy emphasize how much remains unknown about planet formation. Dr. Andrea Isela at Rice University studies protoplanetary disks and notes that while we've identified many planets in the process of forming, the specific mechanisms by which dust grains stick together to form kilometer-sized planetesimals remain poorly understood. Dr. Nienke van der Marel at Leiden University researches how substructures in disks relate to planet formation and finds that even with ALMA's resolution, we can't directly observe planet assembly at the scales where it happens. The implications for Earth science come through interdisciplinary thinking. Complex systems researchers study how patterns emerge in systems ranging from fluid turbulence to ecosystem dynamics to social networks. The mathematical tools, nonlinear dynamics, chaos theory, statistical mechanics, apply across domains. Insights gained from studying one complex system can inform approaches to others. Understanding swirling dust clouds around distant stars might seem irrelevant to predicting winter storms on Earth, but the underlying challenge is identical: extracting predictable large-scale patterns from turbulent, chaotic, small-scale processes. Astrophysicists and meteorologists solve similar equations, just with different boundary conditions and forcing mechanisms. What's next in planetary formation research includes upcoming missions and telescope capabilities. The James Webb Space Telescope observes protoplanetary disks in infrared wavelengths, revealing temperature structures and chemical compositions invisible to ALMA. Ground-based telescopes with adaptive optics achieve higher resolution imaging. Theoretical work improves our models of how gravitational instabilities create structure in disks. Within the next few years, we'll likely identify planets in the act of forming rather than just inferring their presence from disk features. Each discovery reshapes our understanding of how common or rare Earth-like planets might be, which feeds into questions about life in the universe. But more immediately, these studies remind us that the processes building planets are still active throughout the galaxy. Formation isn't a historical event that happened once and finished. It's ongoing, observable, and dynamic. There's a humbling quality to watching planet formation unfold across millions of years while we struggle to predict next week's weather. The timescales differ by factors of billions, but the fundamental challenge persists. Complex systems, governed by understood physics, still generate outcomes we can't fully anticipate. The universe doesn't resist our understanding maliciously. It's simply too intricate for complete prediction, given the computational resources available to us. From swirling clouds of dust around distant stars to swirling masses of ice and air crossing Earth's surface, patterns repeat because physics repeats. Understanding those patterns requires both reductionist analysis, breaking systems into component parts and studying their interactions, and holistic synthesis, recognizing emergent behaviors that can't be predicted from components alone. We're getting better at both, slowly, through patient observation and careful modeling. Which brings us to another frontier, where observation meets pattern recognition, where human ingenuity amplifies our ability to see what was previously invisible. Artificial intelligence systems can now detect cosmic events from minimal data, identifying patterns in electromagnetic signals that human astronomers would miss or take months to find. A research team recently demonstrated that machine learning algorithms trained on simulated supernova light curves can identify real supernova from just a handful of data points, sometimes as few as 3 or 4 observations. This matters because telescopes generate vastly more data than humans can analyze, and time-sensitive phenomena, supernova, gamma-ray bursts, gravitational wave counterparts, require rapid identification and follow-up. The breakthrough relies on pattern recognition. AI systems learn what a supernova looks like as it brightens and fades over days or weeks. Not the specific details of any individual event, but the general shape of the light curve, the color evolution, the spectral features. Once trained, these systems scan incoming telescope data and flag candidates for human review. The process turns months of analysis into hours of computation. Translating this technology for non-experts requires analogy. Imagine trying to identify a specific type of bird from a quick glimpse. Maybe you see a flash of red and a particular flight pattern. An experienced birder might recognize the species instantly from those minimal cues. AI systems learn to do similar recognition with cosmic events, identifying supernova, pulsars, or exoplanet transits from fragmentary observations that wouldn't give a human enough information to make a confident identification. The connection to weather forecasting and storm analysis becomes clear when you consider the underlying mathematics. Both domains involve time series data, pattern recognition in noisy signals, and prediction from incomplete information. Meteorological AI systems already help identify severe weather signatures in radar data, predict storm intensification, and optimize forecast models. The techniques aren't identical to astronomical applications, but they share conceptual foundations in machine learning and statistical inference. Real examples demonstrate the power. The Zwicky Transient Facility, a sky survey telescope, generates hundreds of thousands of transient alerts each night. Most are known objects, instrumental artifacts, or uninteresting variables. AI systems filter this flood down to a few hundred promising candidates for human follow-up. Without machine learning, astronomers would drown in data. With it, they focus attention on genuinely new or unusual phenomena. Similarly, the Vera Rubin Observatory, set to begin operations soon, will generate 10 million alerts per night once fully operational. Human analysis at that scale is impossible. AI becomes not just helpful, but essential. The algorithms must achieve high accuracy, because every false positive wastes telescope time on follow-up observations, and every false negative means a potentially groundbreaking discovery gets missed. But AI isn't magic, and its limitations matter. Machine learning systems excel at interpolation, making predictions within the range of their training data. They struggle with extrapolation, handling conditions that differ significantly from what they've seen before. A storm more intense or unusual than anything in the historical record might break AI prediction systems because they have no template to match against. This is precisely when you need forecasts to be most reliable. Ethical and societal implications arise when we delegate critical decisions to algorithms. If an AI system predicts infrastructure failure and recommends preemptive power shutoffs affecting millions of people, who's accountable if the prediction is wrong? If storm forecasting AI generates an evacuation recommendation that proves unnecessary, who bears responsibility for the economic and social disruption? These aren't just technical questions. They're governance questions about human oversight of machine intelligence in high-stakes contexts. Transparency becomes crucial. Black box AI systems that make predictions without explainable reasoning create trust problems. If an algorithm says a supernova is likely forming in a distant galaxy, astronomers want to understand why the system reached that conclusion, which features in the data drove the prediction. Similarly, grid operators need to understand why an AI flagged specific equipment for urgent maintenance. Explainable AI research addresses this by developing methods that reveal how models make decisions, but the field is still maturing. Future prospects in AI-assisted science and infrastructure management include near-term advances likely in the next few years. Astronomical surveys will generate petabytes of data requiring automated analysis. AI will become standard in identifying candidates for follow-up, classifying transients, and even controlling telescopes to autonomously decide what to observe next based on previous detections. This closes the loop from detection to characterization without human intervention, except at strategic levels. For infrastructure, real-time monitoring systems integrated with AI prediction could enable proactive grid management, rerouting power before failures cascade, scheduling maintenance when risk algorithms indicate highest priority, optimizing resource allocation during emergencies based on predicted demand. The technology exists. Deployment requires investment, regulatory frameworks, and cultural shifts in how utilities operate. Wrapping back to Winter Storm Fern, imagine if AI systems analyzing atmospheric data, grid sensor networks, and supply chain logistics had predicted the combined impact days earlier with greater precision than human forecasters achieved. Emergency managers could have pre-positioned resources more effectively. Utilities could have preemptively hardened vulnerable grid segments. Residents could have received clearer guidance about preparation needs. Maybe the outcome would have been significantly better? Maybe not. Some infrastructure failures were inevitable given decades of deferred maintenance. But better information creates opportunities for better decisions. The connection from planet formation to storm patterns to AI detection closes a conceptual circle. Complex systems governed by physics generate patterns. Observing those patterns requires sophisticated instruments generating vast data. Extracting meaning from that data requires both human insight and machine computation. Understanding emerges from the interplay between observation, theory, and analysis. We study dust clouds around distant stars to understand how planets form, including our own Earth, billions of years ago. We study atmospheric dynamics to understand storms like Winter Storm Fern. We develop AI to help us see patterns in data too voluminous or subtle for unaided human perception. Each domain informs the others. Each advance opens new questions while answering old ones. The universe presents us with complexity at every scale, from subatomic particles to galactic superclusters, from microseconds to cosmic epochs. Our tools for understanding that complexity keep improving. Telescopes see farther and clearer. Sensors collect more data. Computers process information faster. Algorithms find patterns we'd never notice. Yet the frontier of the unknown keeps expanding faster than we can map it. Winter Storm. Fern happened on a planet orbiting a star in a galaxy containing hundreds of billions of other stars, many with their own planetary systems, some likely experiencing their own weather patterns, governed by the same physics that creates storms here. The ice that paralyzed American cities formed from water molecules that have cycled through Earth's atmosphere, oceans, and crust for billions of years, perhaps originating in comets that bombarded the young planet during its formation from a protoplanetary disk not unlike those we now observe around distant stars. Understanding chaos, from weather patterns to cosmic evolution, may be humanity's greatest intellectual frontier. Not because we seek to eliminate unpredictability, which may be impossible, but because we need to navigate it. We build societies, infrastructure, and lives that assume a certain degree of predictability. When that assumption fails, people die, systems collapse, and we're reminded that our control over nature is limited and provisional. The storms will keep coming. Some will predict accurately, some will surprise us. Infrastructure will fail until we invest in making it resilient. Climate will continue changing in ways that challenge our preparedness assumptions. The universe will keep generating phenomena that exceed our models and violate our expectations. But we'll keep observing, learning, adapting. We'll develop better forecasts, stronger infrastructure, smarter algorithms. We'll study planet formation to understand Earth's origins and atmospheric dynamics, to understand tomorrow's weather, and AI to help us see patterns connecting them all. Because in the end, that's what science is. Humanity's ongoing conversation with reality, asking questions, testing answers, discovering that every answer breeds new questions. Winter Storm Fern asked us hard questions about infrastructure, preparedness, climate, and resilience. We're still formulating answers. And somewhere in a protoplanetary disk hundreds of light years away, a planet is forming that billions of years from now might have its own storms, and perhaps its own observers wondering how to predict them. The patterns repeat. The questions evolve. Understanding remains perpetually just beyond our grasp, pulling us forward